every time you have a vector, it starts at the origin, ends at the point, and you have a magnitude and a direction. The direction is usually denoted by an angle. If it's north, south, east, or west, there's still an angle for that. There's 90 degrees for north, 180 for west, 270 for south, and 0 or 360 for east. If it's northeast, you know how to get it. Northeast, you have to know, if it just says northeast, that's 45. If it says northwest, that's 135, etc., etc. But usually, they will give you the exact angle. Anyhow, so all vectors have a component on x and a component on y, at least in a two-dimensional plane, which is what we're discussing. We have an x component and a y component. So, how to get from the regular vector, how do you get your x component and your y component? So, I know I've already written the formulas here, but let's try to look at it now. So what we're given is our angle and our vector. What we want to find out is this and this. So what we have to use is, unfortunately, trigonometry. Trigonometry, in the trigonometric ratios, sine of theta is equal to, what is sine of theta? It's equal to.
Wait, are you talking about the angle or?
Yeah, sine of theta. Theta is the angle.
Sine theta.
So katawa, guys. We're trying to solve for this using this.
Oh, you're talking about that. Okay, sorry.
So sine theta is equal to, we know that this is our v sub x and this is our v sub, this is our v sub y and this is our v sub x, right?
Yeah.
We know this and this, we don't know this. Sample. We have a force vector. Force is is newtons, right?
Yeah.
10 newtons in the direction of 30 degrees. 30 degrees.
Yeah.
So our theta is 30 degrees, our v is 10 newtons. We want to look for, say, v sub y. So we know that sine theta is equal to opposite, which is v sub y, over hypotenuse, which is our v. Since we're looking for v sub y, we can transpose v to the other side. That becomes v sine theta equals v sub y, which is how we get this one. If we're looking for x this time, we just have to look at cosine theta is equal to adjacent over hypotenuse, v sub x over v, and since we transpose, we get this also. V sub x equals v cos theta. Yes. However, this only works if you have your theta expressed in the regular form. What is the regular form? It means that if you have a vector like this, your theta is this one. If you vector like this, your theta is this one. Not, if your angle given is, say, 50 degrees south of east, 50 degrees south of east, you don't use 50 as your theta when using these equations. That will give you an immediate wrong answer. Yeah. So this is your south of east, right? This is 50 degrees. Technically, what you can do is you can use negative 50, since that is still technically regular form. But what is much easier to understand and comprehend is if you make it like this. So that would be 360 minus 50 degrees, which becomes 310 degrees. This is our angle if it's 50 degrees south of east. Okay, next. Okay, what else? So we have the angle. You have to know how to convert the angle to normal form, which starts at the x-axis and goes counterclockwise. Any questions as of how to do that? What if I write 25 degrees south of west? How do you get that?
25 minus, 25 plus 180.
Okay, so the trick with physics it's a lot easier to draw it muna. Like, doesn't have to be exact. So think of it this way. We have our axis. West is here, south of west. So 25. This is 25 degrees. So to get it, 180 plus 185. Any other questions on how to make it? What if I do 50 degrees north of west? Correct, 180 minus 50. If you're confused, try drawing it out. North of west. This is our 50 degrees. This is our 50. Since we're looking for this angle, 180 minus 50. Anyhow. What if I read 20 degrees north of east? That's my 20 degrees. 20 degrees north of east. 20 degrees. Okay. Any questions still? Okay. So once we have our angle and our magnitude, easy lang to get there. Just plug it into your calculator. What if it's the other way around? What if it's the other way around though? What if we're given the vector components but not the actual vector? Example, we have a velocity velocity vector whose v sub x is 10 meters per second, and our v sub y is 20 meters per second. How do we get the origin? How do we get the original? How do we, guys? Even though I'm not a teacher, it's technically a class. How do we get it? It's technically we have our how do we get the final this thing, the magnitude first? How do you get the magnitude of the final vector given the two components? Okay. Yes, correct. If we model it like a triangle, we have our vector, we have our v sub y and our v sub x, and this is a right triangle because it's directions. We can Pythagorean theorem it. V squared equals v sub y squared plus v sub x squared. So again, v will be square root. That's the formula. So if you ever forget what the formula is, remember Pythagorean theorem. Really easy to know. It's really easy to do this. Again, just plug your values into your calculator. However, what if it's, so let's say v sub x is 10 meters per second east, and our v sub y is at 10 meters per second north. It still works in the It still works, right? What if this becomes south, east and south? What value do we plug into into this formula? See, if it's east and north, we just plug it as is, because that's north and that's east. What if it becomes south? Yes, negative. You have to know which way it's going. Usually, well, sometimes, I can't say most of that. Sometimes it'll already be given, your v sub x and v sub y already given, which is positive, which is negative, or both are positive or both are negative. But if you're given your vector components and you're given directions instead, you have to see which one becomes negative. Okay? Quick, easy way to remember is that if your vector, sorry, wait lang. This is still in, we're now in getting the vector from the vector components. Sorry, can we backtrack a little bit to getting the vector components from the vector? If our vector is like that, it's easy to tell that our x will be positive and our y will be positive.
Yeah.
But if it's here, which one will be positive and which one will be negative?
X positive, Y negative.
Yes. In this one, both are negative.
Yeah.
In this one,
X.
y is positive and x is negative.
Oh yeah.
That's an easy way to remember, just by the graph. However, for this one, easy lang to tell based on the direction each component is going. You just have to remember which direction corresponds to negative. Don't forget to flip it to negative if you have to. Okay? Because it will give you it won't give you a different calculation for the magnitude, but it will give you a different calculation for the angle. How do we get the angle given these two? We're looking for this angle given these two.
So basta if it's north or east.
North or east, you can stick with it.
Positive.
If it's south or west, it's negative. That may not be all, because not all fours. No, it's always a direction. It's a vector. Yeah. So northeast is positive, southwest is negative. Also possibly,
So not the phone.
your
Okay, kind of.
That's alright. also sometimes your up and down, your y-axis might not be up, north and south. It might be up and down.
Mosquito.
Just to let you know, y-axis can sometimes be up and down. Okay? Okay. How do we find the angle given these two vector components?
Y over
We need to use trigonometry. Since we're looking for an angle, angles are solved for using trigonometry. So, our trigonometric ratios, so katoa. Which one involves this side and this side? Tangent, yes. So tangent, if we're looking for tangent over theta, that's equal to Vy over Vx. Yes? But we're looking for theta. So what we do is we get the tan inverse of it, which is your tangent negative 1 over that. This is how to solve it. And this is where your signs are necessary. If you put the wrong signs for your vector and components, you'll get the wrong angle. However, so sample, we have not sample. So we have our v sub y and our v sub x. So we get our angle is equal to something, right? Whatever. When we do it, we get our angle. You can just by plugging it. This is the one where if you plug it into your calculator, that might not be necessarily the last step that you do. Because once you get it to your calculator, you get a value, right? So that angle will always be measured in the regular form. So it'll either be however, when your calculator gives an angle result, the angle will typically be the angle will probably be given only in the first quadrant and the fourth quadrant. What do I mean by this? Let me borrow this calculator. Not this calculator, I don't know how to use it. Does anyone have a calculator? Oh yeah, perfect. So, sample. We have our x mode. Sample. We have our v sub x. Let's say our vx is 10 or vy is negative 20. Or let's say our vx is 10 and vy is 20 for now, right? So that's tangent inverse, that's shift and then the tangent button, equals 20 over 10. Remember, for most of your calculations, the y will be over the x, not the x over the y. Make sure it's the y over the x. Okay? Why is that? Because usually, it's rise over run, it's opposite over adjacent, not the other way around. So your y should be over your x in most of the fractions where you do. So your inverse tangent of 20 divided by 10, we get 63.43. So that's 63 degrees, obviously. However, let's see, what if it's here? Our x is negative and our y is positive. Negative 10 over 20. Negative 10 and 20, right? So inverse tangent of 20 over negative 10. What it will give us is negative 63. Negative 63.
Yeah.
But our problem is negative 63 is in the fourth quadrant. But we well know that if it looks like this, it's in our second quadrant. So what we do when we get that is we take the second quadrant. That's 180, right? And since our vector will look something like this, if it's like that, right? It looks something like that. Which one is the negative 63?
The X.
No. Which angle here is the negative 63?
Like that.
Yes.
Yes.
If it's negative, it goes from the right, from the left to the right, from clockwise. So this is our negative 63. So to get this actual angle, what we do is 180 minus that. Or if I don't think you're picky, you could just say 63 degrees north of west. Yes?
Wait, when do you use? Sorry, when do you use the inverse tangent again?
When you're looking for the angle. Because we're looking for the angle.
Yeah.
Since tangent of theta is equal to Vy over Vx, but we're looking for the angle. We don't use just plain tangent. We have to use the inverse tangent. We get the inverse tangent of each side. What we do here is we get the inverse tangent of each side. This cancels out.
Yeah.
It comes like that. So do you get it?
So when making an angle like 63 degrees north, that's north of west, right?
Yes.
You always base it on the x-axis now.
Yeah, it's always based on the x-axis. If it's positive, it's going from this side on the x-axis. If it's negative, it's going from this side.
And also from
Or it also, if it's, or positive can also be going like that way. Negative can also be here. Example, if in this case, our x and y is like this. X is positive, y is negative, right? In fourth quadrant. Negative 63, you got negative 63 degrees in the calculator, like what we just did. So that, since it's already in the fourth quadrant, we know that this is our negative 63 degrees. So you could say 63 degrees south of east. Or you can look for the actual angle if you want. Okay, are you good for the vectors?
Yeah.
One last thing for vectors, addition of vectors. So you remember, this one is, let's start with the graphical representation of addition of vectors. Example, we have our force going this way, and we have another vector going that way. How do we add them? Two ways, tail to tip, we can go like that. And then and then our final vector is like that, right?
Yeah.
Or we can do the parallelogram, where it's like this. We have our vector like that, our vector like that, and then we draw lines that are parallel to them, and then this is our point. It's basically the same thing.
Yes.
But these are just, these are just graphical representations. But usually what you want to do when you add vectors is you want to have exact values, because you won't really get two exact values from the graphical representation. Because we're not sure that this is completely parallel, we're not sure that we drew it exactly correctly. So what we do is addition of vectors. How do you do that? You add their x components and their y components, and then you go. So what you do? Okay, wait, sorry. Am I okay it's okay if I erase this?
Yeah.
Okay. What you do is, so let's see, we have our our FA, FB. Let's make it a bit more complicated. 3 vectors plus FC equals FD, right? So that's 4 force vectors. Example, one's going this way, another vector is going that way, another vector is going that way, right? Especially, that's where parallelogram is a bit hard to do because you have more than 2.
Yeah.
You can't really do parallelogram. Okay. This is a bit too straight. Let's One going that way. Sorry, that's not the same thing. Okay. So what you have to do is you break each one down to its x components. Because we're given FA, FB, and FC. That's usually what will be given. So what we have to do is you break each one down to its separate components. So we break, using those formulas, we get the FAX, FB, FAY, FBX, FBY, FCX, and FCY, right? What you have to do is you add it, just add it. And then we have our FDX, FDY, and then converting it back into what you do is you convert it back into the regular vector form by using the other 2 formulas. Yes?
Yeah.
I can't really do an example right now because we don't have much time left. But, so for this one, Sample, it's in the first quadrant. That means our x and our y are both positive. So you have a positive and we have a positive, right? Easy. When it's in the first quadrant, it's easy lang to convert to this sense, to this way. Say this one is in the fourth quadrant. That means our x is positive and our y is negative, right? Our x is positive and our y is negative, right?
Wrong.
Fourth quadrant? Yeah.
Yeah.
Okay.
Oh yeah.
Sorry. I have to check myself. It's okay. So our x is positive, our y is negative. And then our FC is in the third quadrant. Let's see. If it's in the third quadrant, we have to make it again. There we go. It's in the third quadrant, they'll both be negative. So when you sum it up, you have to make sure to get it the proper signs. Okay? Make sure to make it the proper signs. Okay. Then you get it. And what you do for the final, FD is equal to square root of FDX squared plus FDY squared, etc., etc. This one, to get the angle, it's equal to FDY over FDX, sorry, tangent inverse of FDY over FDX. Right? Guys? So, this one, remember, when you get this, you'll only get the values in the first and the fourth quadrant. But you have to check where it's actually going to be. That's where the graphical one comes in handy. See, because if we get our sample, it's also negative 63. Problem lang, that negative 63 could be in any of these four quadrants. We don't know. So that's where this comes in. That's where graphical comes in. You can draw FA, FB, FC.
Oh, it's there.
It's in this quadrant, pala, or whatever. That's where it comes in handy. So I'd suggest bringing a ruler tomorrow. That might help. Or if not, you can use your ID and just like try to eyeball it, like what you do with the. Okay, that's additional factors. So I couldn't get into it with much detail. I will have to do a really fast review of kinematics.
Let's go.
As in 10 minutes.
Summary na lang.
Like,
If this is the graph,
Of- this is the of what?
supposition time graph.
Okay, yeah, okay. Kinematics equations, they'll all be given, you have them all in your notes, right? Just you have to remember them and how to use them. Our values will usually be A, T, X, X sub 0, V, V sub 0. Or if you prefer, XF, XI, VF, and VI. Okay? Okay. Those are usually the values we're given. That's all that we have. Okay. You have to remember the equations, they'll be given. They'll be given naman.
Okay.
Sir said he'll give it. But V final equals V initial plus AT, we know that, right?
Yeah.
V ano. And then our final position equals our initial position. Our initial position pala plus average velocity times time. Average velocity, okay, this is the trickiest equation to use.
Yeah.
Equals V final plus V initial over 2. Right?
Yes.
Okay, this equation only works. Okay, let's draw a velocity time graph, okay? A velocity time graph. If our velocity time graph looks like this, or if it looks like that, or if it looks like that. Sorry, that's not gonna happen. If it looks like that or like that. If our velocity time graph looks like this,
Total distance.
you cannot use this as V final and this as V initial. You can't use that.
They have to bring the same slope.
It has to be all constant acceleration.
Same line.
Has to be. This assumes A will be constant.
Oh.
And when A is constant, it means that on a velocity time graph, it'll be like that. That's why you can't do average velocity times time for total distance if it's like this.
Hey, which one?
If it's a straight line, that means it's constant acceleration, and you can use this.
Okay.
If it changes speed, like it accelerates at this speed, at this acceleration, until this second, and then it starts going at constant speed, you can't use this. You can't use this.
Wait, so even if he had it constant, then biglang ganun?
The only point where you can use it is is in this section. If it's like this, you can use the average velocity times time, but only for this part. In fact, that's how we're able to use it.
Oh.
Remember, diba, we do the base times height divided by 2?
Yeah.
Our height is our velocity final. But our height is our velocity final minus our velocity initial. Right?
Yes.
And our over 2, the base is time. So velocity final minus velocity initial times time over 2. What's this? That's this.
Wait.
Yo, I got.
Wait.
That's not-
So when we do our base times height divided by 2, when we're solving for distance using the velocity times graph, diba we have a triangle,
Yeah.
and our base is time and our height times 2, base times height divided by 2. Our height is this. Our base is this divided by 2. If you notice, this is average velocity. Average velocity times time is equal to distance. That's how you're able to do that. Just a
Bro,
fun.
I don't get how VF minus VI is the height.
You need to go.
I know.
Unless you want to get picked up in 40 minutes.
Sorry, wait lang. 5 minutes, okay?
Not
Can I
bad.
get picked up now, later?
Wait lang, 5 minutes. Okay?
Sorry, one.
So this, on the y-axis, this is our y-axis, right?
Yeah.
This is our velocity. This will be our final velocity, and this is our initial velocity. If you notice.
Oh.
Okay.
That's it.
Shit.
Really?
Yeah.
Oh, so good.
Yes?
Ganun lang pala yun.
Ganun na. Okay, next.
So is the initial velocity 0?
It might or might not. Usually it's like that.
Oh yeah. Oh yeah.
But when it looks like this,
Basta where the line starts.
yeah. When it looks like this, then what we split it up into stuff like, then what we split it up into like this part, and this part.
Oh, we did.
Okay, anyhow. Okay, solving problems using uniform acceleration. Just look at there's 5 equations. Just make sure, trick is, try modeling it, try drawing it out, and then it'll be easier to see it.
I.
Try drawing it out, make sure you know which equation to use. Each equation is missing one variable. So use the equations that you have the variable for. Example, if we're solving for A, and we have this and this, but we don't have time, there's an equation for that. That's the v squared plus vo squared plus 2a x minus xo.
Yeah.
Since we don't have time, then we're looking for a, etc., etc. Make sure you know which one to use. And then for free fall, remember free fall acceleration will always be negative 9.8 meters per second squared.
Yes.
And then our graphical analysis of linear precision. You already know how to know and interpret each of them, so I won't go through it.
Yeah.
But if this is our position time, this is our If this is our position time, this is our velocity time, and this is our acceleration time. This is what Jerome asked me to do a while ago. So this is, if our position time looks like that, what will our velocity time look like?
Straight line.
Yes. And our acceleration time will look like this. Zero.
Yeah.
If it looks like this, what's our velocity
Wait,
time?
is that a straight line?
Straight line.
Oh.
It's 0, and so is acceleration.
Yeah.
If it looks like this,
Then it's going curve. It's slanted line.
Steep.
Yeah.
you say that.
Yes.
Okay. Tricky question. Gravity.
Oh shit.
Negative 9.8.
So we're here, right?
Yes.
Yeah.
It's always at the bottom one.
So it starts going like that.
Yes.
Like that.
Yes.
What does it translate here?
It's at the bottom.
It's just like
Okay.
that. It's constantly.
Okay.
Like
Since this
that.
is free fall, right?
Yes.
Yeah.
Free fall.
Yes.
We know our acceleration is. We already know our acceleration graph. That's negative 9.8 meters per second squared.
Yeah.
Wait.
Since this is
yeah.
since this is constant acceleration, this line should be straight and it should never break. It should open.
Yes.
So our velocity begins at 0. It looks like it begins at 0. We
But
don't
it's still
know.
zero. Oh. It's still
And it starts going like that.
Oh.
Is it bending or is it a line?
It's a line. It's a line. Sorry, I'm not good at drawing this. Example: what if we throw it up, and it goes down? Like the usual problem. Throw it up and it goes down. What does this mean for this? We already know this is our acceleration time. What does it mean for this?
It's just on the positive side going down.
Yes. We start at the initial velocity and we start going down. Remember, when it's gravity, your velocity time should never change direction. It's always going to be going down because our acceleration was
That was the
Okay, thank you, Juanpa.
Thanks, Juanpa.
Wait, can you say something like, thank you for listening to my TED Talk?
Thanks for listening to my TED Talk.
Okay.
Oh, you're editing this?
No, I'm not.
No,
I
I'm
just
recording
wanted to
it.
hear that.